In this example, I want to think for a moment how we can find the points of intersection between the curves r equals cosine of 2 theta and r equals 1/2. Here we see r equals cosine of 2 theta is this four-leaved rose curve that we've seen before, and r equals 1/2, which is the circle of radius 1/2 that we have graphed here. Well, we can see from the picture that it's going to intersect. The two curves are going to intersect at these 8 points, right? We can see them here. There's 2 in each of the 4 quadrants. Let's think about how we can solve each of those intersection points. First, we can set the two curves equal to each other, or set the two functions equal to each other. And that'll tell us essentially at what two angles cosine of 2 theta will equal to 1/2, in which case it'll then intersect with this curve r equals 1/2. And well, we know for cosine of theta, if it's just we're talking about cosine as a function, it'll equal to 1/2 in quadrants 1 and 4 when the angle is pi over 3 or negative pi over 3. So that gives us 2 theta then would equal to pi over 3 or negative pi over 3. So we can think of two equations there. But that just gives us the solution in the first quadrant. There could be infinitely many others where we add 2 pi k to get more solutions. But let's just, for instance, now think about the first quadrant case where we say 2 theta is equal to pi over 3, so theta is equal to pi over 6. Or here, 2 theta is equal to negative pi over 3, so theta equals negative pi over 6. And we can add multiples of pi to that to generate more solutions. So for instance, here we can get another solution by adding pi to this. So if I take pi over 6 and I add pi, I get 7 pi over 6. Okay, so notice that gave me 2 solutions here. It gave me this one, and 7 pi over 6, it gave me this one over here. I could then do the same thing here. We have negative pi over 6. That would be this angle here in the 4th quadrant. What do I get if I add pi to that? I get the angle over here in the 2nd quadrant. Should be this angle over here is what I mean. Should be 5 pi over 6. Okay. In addition, we have some other points here that we didn't get, because those are going to occur at angles that are bigger than these ones. So we have to kind of keep going around. So for instance, here this was just from 0 to pi over 6, and then as we're curving down here, we'll get a negative value for theta, or for r. And so notice that here this will equal to negative 1/2. The r value will be negative 1/2, and that'll intersect the curve here when r is negative 1/2. So what we could do is we can set cosine of 2 theta equal to negative 1/2, and that'll give us some more solutions. So for instance, 2 theta is equal to negative, cosine of theta is equal to negative 1/2 at angles in the 3rd and 4th quadrants, which are 5 pi over 6, 2 pi over 3 and in the third quadrant 4 pi over 3. Okay, so those will be the angles that give me cosine equal to -1/2. So here, if I now solve for theta, we get theta is pi over 3. And then I can add, because here we can add 2 pi k to get another solution, we can add pi to this, because when I divide by 2, we're adding multiples of pi, and get another one, which would be 4 pi over 3. And then here, I can do the same thing. We divide by 2, we get theta is 2 pi over 3. And then adding pi, we get 5 pi over 3. Okay, and that gives me the remaining angles here, pi over 3, 4 pi over 3 down here, 2 pi over 3 up here, and 5 pi over 3 down here. So we see that that gives us all the points of intersection that we observe in the picture. Okay. So the reason why we equaled it to -1/2 here is because we noticed that the curve is going to pass through negative values of r when it passes through these points on certain portions of the graph. And in fact, r equals 1/2 is the same as the equation r equals -1/2. They're going to form the same curve. Okay. Let's move on to a new topic, which is arc length. And here we can use the strategy that we did when we found the arc length of a curve defined by parametric equations. Here we know that we can find the parametric equations of a polar curve by writing it as f of theta cosine theta for the x-coordinate, f of theta sine theta for the y-coordinate. And so dx over d theta will be f prime of theta cosine theta minus f of theta sine theta. Just doing a little product rule there. And then here for dy d theta, f prime of theta sine theta plus f of theta cosine theta. Okay. And when we insert those values here, okay, we get something that looks very complicated. But luckily, if we were to go through all the algebra and use a little bit of trig identities to simplify it, it actually simplifies into a pretty nice form where we get f of theta squared in one factor plus f prime of theta squared in another factor. Okay, so actually, of course, here I'm skipping a lot of algebra and a lot of simplification that occurs. Okay, but I encourage you, if you want to verify it yourself, just try it out. So you can enter this into the expression here and square it out. So you'll do a little bit of foiling. You'll enter this expression here, and for the dy d theta, foil it out, and then you can probably just follow your nose from there. In other words, you'll combine some terms, factor some common factors out. Whenever you see sine squared plus cosine squared, you can replace that with 1. And then it'll reduce down to this nice simple expression here. And this is what we'll do when we're looking for finding the arc length of a polar curve. So let's practice that a little bit. Or here's it using the r notation, but same idea. Okay, so let's practice this a little bit. Let's find the length of the cardioid. R equals 1 plus sine theta. Okay, so if we've got r equals 1 plus sine theta, what's r prime, or dr d theta? So it'll just be cosine theta. And we know that the whole cardioid is formed with theta going from 0 all the way to 2 pi. So we can just integrate from 0 to 2 pi, square root of r squared, so 1 plus sine theta squared plus r prime squared. Okay, so we can set it up this way. You might also notice that there is some symmetry that you could also exploit as well, noticing that it's symmetric here with respect to the y-axis. So I can integrate, for instance, from negative pi over 2 to positive pi over 2, and then multiply it by 2 to get the whole length. But here, let's work it out this way. Okay, so we've got inside the parentheses here, we'll expand out. 1 plus sine theta will be 1 plus 2 sine theta plus sine squared theta, and then plus cosine squared. And then we will replace sine squared plus cosine squared with 1. So that becomes 2 plus 2 sine theta. Now let's think about how we can evaluate this remaining integral. And one trick we can do is sort of like a conjugate trick. In other words, I can multiply the integrand here by square root of 2 minus 2 sine theta. Let's work it out up here and see how that actually simplifies. So it's like I'm multiplying the top and the bottom by 2 minus 2 sine theta. How does that work out? When I multiply these two square roots in the numerator together, we get 4 minus 4 sine squared inside the square root, just foiling those guys out. When I factor out the 4, we get a 2 on the outside. And 1 minus sine squared becomes cosine squared, which when we take the square root of it just becomes cosine. In fact, here's where I've got to be a little bit careful. If I take the square root of cosine squared, technically it should have absolute values on the cosine, but if we choose a region where cosine is always positive, then we can ignore the absolute values. And so that's where actually the symmetry might become useful. So if I change this so that we're looking at the region where cosine is always positive, so do 2 times the integral from negative pi over 2 to positive pi over 2, instead of from 0 to 2 pi, then we know cosine is always positive, and so we can remove the square here from the cosine without having to worry about absolute value. And then, oh, sorry, this should be sine theta down here, not cosine theta. Okay. And why is this better? Well, now, actually, it's in a form where we can substitute. I can let u equal to 2 minus 2 sine theta. And then the derivative will be a multiple of cosine theta that we have up here. So let's see what we get now. So our integral now becomes, let's see, we get 2 cosine theta d theta becomes negative du, so I'll put a minus 2. And then we got 1 over the square root of u, or here I'll just write u to the negative 1/2 power. integrating that will become 2u to the positive 1/2. Here I'll put the u back in so we can evaluate it. From negative pi over 2 to positive pi over 2. Sine of pi over 2 is 1. So we got a 2 minus 2, which is 0. So minus negative 4, so plus 4. Sine of negative pi over 2 is negative 1. So that'll be 2 plus 2 there. So we got 4 times the square root of 4 is 2, so we got 8. Okay, so that tells us the length all the way around this cardioid is length of 8.